All right, this podcast is going to talk about pressure. What does pressure actually mean? Well, pressure is a unit of force per unit of area. So you can see here in this situation, we have two things that have the exact same amount of force, each having 1 kilogram of mass. But one on the left is going to be spread out over a larger surface area versus the one on the right, which is condensed into a much smaller surface area. So the one on the left would have less pressure than the one on the right. This is why someone can lay on a bed of nails, because the nails are all spread out over the entire surface of the body versus someone who lays on just one nail and puts all their weight in that one small area. Now there's a specific unit of pressure that we're going to talk about, and if we have 1 Newton, which is essentially 2.2 pounds, and we spread it over 1 square meter, that's what we call a Pascal. 1 Pascal is 1 Newton per square meter. To talk about gas pressure and air pressure, which is a very important topic for a lot of things, we look at the gas particles of air that's sitting there, and gravity will pull them down, and when they pull them down, they compress against each other. So someone at sea level will have a lot higher atmospheric pressure than those on top of a mountain or something like that. This is a lot more easily recognized in a swimming pool. When you're swimming on the surface, you don't feel much pressure, but if you dive down deep, you do feel a lot larger pressure on your ears and on your body. That's because water is a lot more dense than air, so the effects are much more dramatic. But this is still something that happens in air, and you need to keep that in mind, that pressure is greater the closer you get to the surface of the earth, and less as you get to the top of a mountain. So this is the first barometer ever created, a thing that measures atmospheric pressure. What they did was they took a tube that you can see, and they created a vacuum of it, generally by evacuating the air inside of it. And what they did was they stuck it into a pool of mercury. The atmospheric pressure from outside was pushing the mercury down, and it will push that mercury up into that tube. At sea level, under normal standard atmospheric conditions, that mercury rose 760 millimeters up into that tube, which is why we consider that to be standard atmospheric pressure. If we were on top of a mountain, there would not be as much atmospheric pressure, and the mercury level would not rise as high. If we were below sea level in, say, New Orleans, that mercury level would actually rise even higher. So there are a lot of units of pressure out there, and either you can find these on the internet, or perhaps your teacher gave you some sort of formula sheet. 1 atmosphere of pressure is equal to that 760 millimeters of mercury, also called 760 torr, named after Torricelli. It's also the equivalent to 101,300 pascals, or 101.3 kilopascals. And if you're from America, we usually use PSI, which stands for pounds per square inch, and that would be 14.7 PSI. These are all equal amounts of pressure, just in different units. We'll use these later to convert one unit into another. Say you wanted to test the pressure of a basketball or the pressure in your tires. We use a concept based on a manometer. A manometer is just a way to check the pressure of something and compare it to the atmospheric pressure. If you look on the left one, the U-tube there has both sides open to the atmosphere, and the atmospheric pressure on both sides is exactly the same, and we'll be pushing that level of mercury the same on both sides, which is why there's no difference in the level of the mercury in that U-tube. If we go to the middle situation, imagine this was a straw or something like that. The left side has got pressure put on it, and the right side just has atmospheric pressure pushing on it. So when I blow through a straw on the left side, my pressure is more than the atmospheric pressure, and it'll cause that mercury to rise on the right side. If you look at the situation on the right, this would be like sucking through a straw. I'm creating a vacuum on the left side, but the atmospheric pressure is exactly the same on the right side, so that causes the atmospheric pressure to be more than the pressure that I have while sucking through the straw, which causes the mercury to be pushed up on the left side, causing a difference in height of the mercury column. If we know the atmospheric pressure and we know the difference in height, we can find out the pressure that we are putting on the straw or what the lack of pressure we're putting on the straw. Here's an example manometer problem to see if you can figure this out. A manometer is hooked up to a container seen on the left here. If the barometer of the atmospheric pressure is 760 torr, what is the pressure inside the container in kPa? So I know that the atmospheric pressure is 760 torr, and I notice that there is a difference in the height of the mercury column of 30 millimeters. So remember, 760 torr is the same thing as 760 millimeters of mercury. If the atmospheric pressure is 760 millimeters of mercury, then the container must be 30 less, or 730 millimeters of mercury, which we're going to call 730 torr. So that's the pressure inside the container. But notice that the problem wants it in kPa, or kilopascals. Well, if we go back to our chart, we remember that 760 millimeters of mercury is equal to 101.3 kilopascals. So we can set up a proportion and figure out the pressure inside the container in kPa. So here I've set up the equation. You'll notice that on the right side, I've got the conversion, 760 torr is equal to 101.3, and then I line up the torr on the left side, 730 of our container, over x in kPa. And when I solve for that, I find out that the pressure inside the container is 97.3 kPa. Well, now we know about atmospheric pressure, and we know about all kinds of pressure and air pressure and things like that. But remember that air is a mixture of many different gases. So what we can do is each gas is putting a certain amount of pressure on the container. And when you add all of those pressures of each individual gas up, we end up getting the total air pressure of that situation. For example, here, you'll see the pressure of hydrogen, which we call the partial pressure of hydrogen, is 2.9 atmospheres. And the partial pressure of helium is 7.2 atmospheres. If we add those two pressures together, we get a total pressure of 10.1 atmospheres. Now, what I want you to look at is that there are 0.60 moles of hydrogen and 1.50 moles of helium. So there's more helium in there, hence the reason why it has more pressure. So of the 2.10 moles of gas total in the container, most of it is helium, which is why the pressure is more for helium. So based on the Dalton's law of partial pressure, as long as we know the total pressure and the partial pressure, we can find a relative amount of moles of the gases inside that container. Or if we know the relative amount of moles, we can kind of figure out their partial pressures. Here's a nice simple example to show you what I mean with Dalton's law of partial pressure. If we know that that a flask has air in it of 0.70 atmospheres, and another flask has a just hydrogen gas in it, and I take the two flasks and I mix them together and pour them in their own little flask here, you'll notice that the total pressure inside the new flask is 1.10 atmospheres. Well, if the air was 0.7 and the total was 1.10, then the pressure must be of hydrogen 1.10 minus 0.70 atmospheres, giving us a partial pressure of hydrogen of 0.40 atmospheres of pressure. So as long as you know the pressure of one, you can figure out the pressure of the other, as long as you know the total pressure of that container.